Welcome everybody to this week's Ask an Astronomer episode. My name is Stefan. I'm here with Andy. We are both from the Institute of Astronomy at the
Hello.
University of Cambridge. And we're here to answer all your questions about science, the universe, and everything. Andy, do you want to introduce yourself and tell us a bit about what you're working on?
Yeah, sure. So I'm Andy. I'm a first-year PhD student. So I'm looking at polluted white dwarfs. So what that means is, a white dwarf star is essentially a dead star, but it's just a really dense remnant. So something like the size of the Earth, but imagine the mass of the sun in that small space. So they're really dense, with a really pure atmosphere most of the time. Sometimes you see all kinds of elements in there that shouldn't really be there at all. And it turns out that what you're seeing is dead planets or bits of rocky material that have fallen in to the white dwarf atmosphere. And from looking at those, you can see, or you can try and work out what the material came from and what its formation history was. So that's what I'm trying to do. I'm kind of looking at dead planets, which is pretty cool, I think.
That's nice, yeah. We just got our first question. What is an
Cool.
exoplanet? So do you want to go ahead and tell us a bit about the background?
Sure. Okay. So an exoplanet is just a planet that orbits a star that's not our sun. So there's 8 planets that orbit our sun. So Pluto does not count, which I know got some people got very emotional about that, but it doesn't count. But in fact, that's only a very tiny proportion of all the planets that we know exist. So I think we now know that there's about 4,000 planets that orbit other stars out there in the galaxy, and that number's going up all the time. And these planets, I guess one of the main things that we've learned over the last 20 years or so is that these planets are quite there's some different types of planets that we don't see in our solar system, which is quite interesting. So one of the first exoplanets that was found, in fact the first one that was found around a solar type star, you have it on the slide there, it's called 51 Pegasi b. This is a type of planet called a hot Jupiter. So it's a planet that's kind of the size of Jupiter in our solar system, so really big compared to Earth. But in our solar system, Jupiter is quite a long way from the sun. But 51 Pegasi b is really close to its star, so it's really hot. Hence the name hot Jupiter. And that's quite interesting because that's a type of planet that we don't have in the solar system, but they seem to be actually somewhat common around other stars.
Yeah.
And there's a whole bunch of other types of, well, maybe not a whole bunch of other types of planets, but we see
I think
diversity
you
in
could
exoplanets,
always
which
say
is
a
pretty
whole
cool.
bunch of. That's always a good choice.
Well, maybe it's not a very technical term, but
Yeah, that's true. I mean, we're
it's a
doing.
really interesting field, though.
We are on the Ask an Astronomer live stream here. You don't have to be technical, so that's great.
I'm not sure if I could be.
So right, you mentioned that just like on the solar system, we have all the gas giants are like kind of out in the solar system. So we have those 8 planets: Mercury, Venus, Earth, and Mars. They're all kind of rocky, like they're made of rock and water and Earth and stuff like that. And
Yep.
all the outer planets, so Jupiter, Saturn, Uranus, and Neptune, are all made of gas basically. So they're what we call gas giants, although they all happen to be really large. And yeah, like we thought, oh, maybe it's always the case that the rocky small planets are close to the sun and the large gas giants are, well, far away. But it turns out that there are other solar systems that are very different. And we are just looking at our special case until now.
Yes.
Um,
Which makes sense to do, I think.
yeah, it's a great thing.
but-
Like I think that's like one of the important things in science, right? You have your one example, but you can't just take this one example for granted. You have to find like kind of independent samples, independent confirmation. And you can't just like look at your own planet or your own solar system and think everything else is the same.
And I wonder if the same thing might happen when looking at life. So, for example, when we think about life on other planets, it's logical and it makes sense for us to assume that there's going to be something life as we know it on Earth, where it's kind of all based around water.
Yeah.
That seems to be the most sensible thing to assume. Maybe when we find life one day, fingers crossed, we might find that it's something completely different.
Yeah,
that's really exciting, though.
That would be really cool. Okay, so we got one question quite early that was, is it really possible to get a PhD in a student state? I think what you're referring to is that, so in the UK, PhD, well, when you're doing a PhD, you're considered a student. So, I mean, we call ourselves PhD students here, while in many other European countries, especially, the PhDs are more considered to be kind of staff, like people who get a salary and are working for the university. They're doing like work like correcting exams or exercises, and not kind of like considered student, but more like kind of behind being a student. I think this is like kind of a conceptual difference. It makes a bit of some slight differences in kind of administration, and like, you know, you call students instead of I don't know, PhD candidates, but it doesn't really make that much of a difference in practice. Like, you still just spend most of your day doing research, spend a bit of your day doing teaching and outreach. So it's basically the same in practice, up to like some more differences. Oh yeah, fees is a thing, but let's not discuss this now. But otherwise, I think it's quite similar in practice. Yeah, let's see if we get our PhD in 3 years then. Okay, so before we start with the dark matter question, maybe we take one more stars and planet question. How did heavy metals, such as gold, reach the planets after they were formed from a neutron star merger? I'm guessing these heavy planets aren't floating around space. I guess you mean metals there. So maybe I should give a bit of background here.
Yeah.
Or do you want to give some background? Okay, so I'm the cosmologist here, right?
You might know more about neutron star mergers than me. Yeah.
When the universe was when the universe began, right, at the Big Bang, everything was full of well, actually, yeah. I mean, the universe started with like protons, neutrons, and all the elementary particles. But after some point, they formed all into hydrogen, helium, and a tiny amount of lithium. So we only had 3 types of stuff in the universe. That's what we call light elements, or mostly, let's say, hydrogen and helium, so 2 types of stuff. And at some point, some of these materials got converted to heavier stuff. And it's not easy to make heavy elements such as gold, because it needs energy to convert those light elements to heavy stuff as gold. So you cannot do this in like a normal star, but this only happens in really kind of extreme events, such as supernovae or bigger explosions, neutron star mergers. So when 2 like really small stars collide together and you get a huge explosion. In these events, everything we are made of except for hydrogen and helium are created. Well, a few elements like carbon, nitrogen, oxygen, iron, I don't know, a few others are created in normal stars, but most of the exciting elements come from explosions, supernovae, etc. And the question is now, how do we get those elements to the planets, right? I mean, if you go on Earth, you dig a hole and you can't find gold. Well, if at the right place. And so this gold has to somehow get from the supernova explosion to us. And I'm not really an expert on this. I'm not sure if you know that, Andy. I think it's mostly how the kind of stuff gets from the supernova to the planet. I think it's just when you have a supernova. So it's not the okay. So to make this clear, the supernova doesn't like make stuff fall on a planet that already exists. Usually you have a supernova, and then you have a huge cloud that is full of various materials. So you not only have the hydrogen and helium, but you also have all the metals that the supernova just like spread out in the universe. Because the supernova is a like huge explosion. So there's not like a clump of metal lying there at the end. It's just like scattered all over the place. And then in this cloud, eventually a new star forms. And around this new star, you get the disk, and then planets form out of this disk. So the material is already there, and it's all like distributed around. And then the planet forms and already contains all the elements. And that's, I think, how it works.
Yeah, that's pretty much my understanding as well. It will just form out of whatever material happens to be there. Something that might potentially be worth mentioning is that you can only go up to iron in these when you make these elements. If you go beyond iron, you start requiring more energy than you can actually release.
Yeah,
by,
right.
by fusion. So
That's also a really interesting fact, yeah. Oh, we got a lot of questions, and we already got the question, what is dark matter twice, so I'll just go ahead and answer that now.
yeah, the people really want to know. You better answer.
So we don't know what is dark matter. That's the first disappointment I have to give you. But we're pretty sure it's there. Quite sure, actually. So what we do is the following: we just look out in the universe and we look for all the matter that we know. Right? We know from Earth all the matter. We know the standard model of particle physics. So we know there are protons, there are neutrons, a few other things, and they form atoms like hydrogen, helium, lithium, all the other fun in the periodic system. And when we look into the space, for example in the galaxy, and see how the stars rotate, and we look at all the mass we see, and we run the calculation we see, the mass that is there in the galaxy is not enough mass to make the stars rotate in this way. And that was actually discovered quite early, I think almost 100 years ago now. I think it was like in the... Actually, I don't know how many, but many tens of years ago. I think it was Zwicky and Vera Rubin that made those discoveries. Anyway, by now we have...
We're astronomers, you can just say like tens. Then the actual number doesn't matter.
That's true. So by now we have even more observations, so I won't go into all the details, but for example the fact that within about 13 billion years, that's how old our universe is, we actually form things like galaxies. This would not work if you didn't have dark matter. You need this dark matter to kind of pull everything together. So that's also one hint we know, that there must be something that's pulling stuff together, but that's not the matter that we see, because there is not enough matter that we can see. And yeah, so that's basically why people said, okay, let's just postulate there's a stuff called dark matter, and it does not interact with other stuff. So when dark matter comes, let's say there's a football made out of dark matter flying through me, I wouldn't know this at all. Like, no way. Because it doesn't interact with me. It's not like, a real football, which would interact electromagnetically with me. So the atoms of the football and the atoms of my arm would interact, and it would hurt. But with dark matter, nothing happens. So that's kind of
There'd be some gravitational interaction, right? But
exactly, right. Weak. So the gravitational interaction would be there. But, well, a football of dark matter is as heavy as a real football, which is not very heavy, and you cannot feel the gravitational force of a football. You can feel the gravitational force of a planet. So when a dark matter Earth would fly past Earth, we would notice, because it would suddenly, be pulled up to the top or to the side. So that would be measurable. And yeah, there are many experiments to try to detect dark matter. So, like, various experiments try to just have a really accurate, like, let's say a huge tank of water, and wait until dark matter flies through it and hope maybe one of those dark matter particles will interact with one of those many trillions of water particles or xenon particles or something, and just try to go, like, to be really sensitive and to have really large numbers. But we have not yet found what is dark matter or what particle makes dark matter. We just know there must be something that is, like, kind of making gravity but not making usual interactions. Okay, now while I was talking, there are so many questions. That's great. Thank you for all the questions. So we get... oh, there was a question about dwarf planets. So do you know something about dwarf planets? Because I do not know a lot. We were talking about Ceres, Haumea, Eris, Makemake, or I'm not sure what's the correct pronunciation. Pluto. Do you know more dwarf planets, or do you know how many there are in the solar system?
I feel like I should do, but
I'm not sure if do you know if the Pluto has this companion Charon, right? That's within its orbit. Yeah. It's like orbiting. Is this thing a moon, or is it also called a dwarf planet? Because it's almost as large as Pluto, so I'm not sure if it's called Pluto's a dwarf planet and that it's moon, or as a planet.
Yeah, it's an interesting point. I guess it's just a semantic question, really, but you could maybe refer to Charon as like a satellite, and that sort of makes it nice and vague.
Okay.
I guess they're a comparable size, I think. So it seems plausible, but Charon might also potentially count as a dwarf planet, like the same as Pluto. But to be honest, I don't know.
Okay, so
Ceres,
yeah.
Ceres, I think, is a dwarf planet.
Yeah, I think those are all dwarf planets.
Is a...
Aren't there?
Is Makemake a dwarf planet?
Well, okay, I guess that's something for the
I don't want
Wikipedia
to
look up
commit to saying
afterwards.
something because I might be wrong.
So yeah, regarding if there's all the dwarf planets, I'm not sure if there are more, or like if for that particular one if there are dwarf planets. Yeah, we can probably Google it afterwards. Otherwise, I'm not like I think it would be really surprising if we discovered all the dwarf planets, because they are, well, kind of small, and there might be some in the kind of outer solar system. We're probably quite sure that there are no ones that are really close. Like Ceres, I think, is in the asteroid belt and is quite close, relatively speaking. So I guess if there would be more of kind of that close, we would have found them. But far away in the solar system, we don't even know if there's a ninth planet. Like there are some studies suggesting that there might maybe be a ninth planet that we didn't discover, ominously called Planet 9. So yeah, there might be other dwarf planets as well, but we didn't. Yeah, we're not sure.
Yeah.
Okay.
Sedno is a maybe one that I've just thought of that could go onto our list, I think. But,
sorry?
I think Sedna is another one that might be on that list.
Right. I forgot that.
I could be wrong, but that's another name
I remember
I have
the
in my
name
head
as well.
somewhere.
Okay, there you go, another dwarf planet. Okay, so we got one follow-up question regarding our Pegasi 51b discussion. So we discussed a bit earlier with one question: what does this name mean? This name that we have here on the poster.
Yeah. So with these names, the star is called 51 Pegasi.
Mm-hmm.
And I think that's why is it called that? I think the Pegasi might be a reference to which constellation it's nearest to in the sky. I think that's probably what it is, but I don't want to be 100% on that. The B at the end is the naming convention is you add a letter to the end according to the order the planet is away from the star, if that makes sense. So if you have 3 planets around a star, let's say the star was called 51 Pegasi, you would call them 51 Pegasi B, 51 Pegasi C, 51 Pegasi D.
Okay, I see.
So Earth would be Sol D, I guess, by that logic. You go Sol for the Sun, and then Sol.
So the Sun itself basically is A, right? And then the first planet is B.
Yeah, so yeah, A is reserved for the star in this case, and then when you're looking at the planets, you'd go down to B. But B could also be, in general, like a smaller companion. So if you had a heavy star and a lighter star, then the lighter star could be B. So Sirius A and Sirius B, for example.
Ah, yes, right. Okay. So what if we discover a new exoplanet that's closer to than all the others? Do we have to rename them all, or is there some exception in the rules?
I guess you probably would have. Well, I don't know.
I guess we would make an exception if it was so, right?
Ideally, you would. I guess ideally you would rename them all, but it might be confusing to rename them. You might just.
Yeah.
You might just make an exception depending on how well known the system is.
Yeah, I think if you have tons of papers about this one planet, and then you have to rename it, it's gonna be a mess.
Yeah, it'll be very confusing for anyone trying to read about it. But it's less likely that the closer a planet is to its star, the easier it is to find it. So it's more likely that you'd have to add a new letter onto the end rather than change all the letters you've already got. So if you named it in reverse, starting with the outermost one, then you'd have some real problems potentially.
So hopefully someone thought about this, and then they made the naming convention at least the good way, the common sense way.
Yeah, it could be worse.
Okay, so we got a question about Hawking radiation a while ago. So let me start from the beginning. Hawking radiation is something that comes from black holes. So for those of you who haven't been here that much, because I think we get asked every week about black holes, but I'm happy to explain it again. When you have, let's say you have Earth, and you want to escape from Earth, you need a certain velocity, right? Because Earth has a gravity force, and you need some velocity to get away from Earth. And that is true for, like rockets, people on rockets, etc. But that's also true in a slightly different way for light. So when you have a light ray and you shoot it away from Earth, it loses a bit of its energy going out from the Earth. So on Earth, let's say it has, I don't know, 1 joule of energy. I have no idea how much this is for a photon, probably a lot. Actually, it's quite a lot. Anyway, and then it goes out of Earth, and it will have 0.99 something joules. So it will lose a tiny amount of energy. But its speed will be still the same, but it will just lose a bit of energy. And now you just go up and make this planet bigger and bigger. So if you have something like the Sun, it will already lose a bit more energy. If you have something like a, I don't know, neutron star, it will be quite a lot of energy. But if you have a black hole, the black hole is so heavy that it stops the photon completely from going out. So yeah, there's a certain radius of a black hole that's called the Schwarzschild radius. And if you are close enough to the black hole, so within this radius, then you cannot escape anymore because the gravity force is so strong. And even light could not escape from a black hole. So it would just kind of get well, it's hard to describe in nice terms. You could say like it would get, okay, so as an example, if you would have light that is just on the edge of the black hole and you would kind of shoot a laser array from the black hole, it would kind of get stuck on this edge. So it wouldn't be able to pass this edge and would just get kind of slower and slower. It's really weird. Black holes are really weird. The point is nothing can come out. And now this you combine this really weird phenomenon with quantum physics. In quantum physics, everything is a bit uncertain, right? Heisenberg told us this. There's this uncertainty principle, and the universe isn't that exact when it comes to really small things. So what you can do is you can borrow a bit of energy from the universe and create two particles, have a bit of fun, and annihilate them again, and the energy goes away again. So you can kind of have small fluctuations, is what we call this. So there could be a particle existing, now it stops existing, another particle appear, it goes away again. And this is just fine in the normal world. You can actually measure this. There's this thing called the Casimir effect, which is really cool. You can have like two plates that hold really close together, and you can measure that there are like particles being created in between, just out of the vacuum. But that's not what we're discussing now. So now you do this close to a black hole. And now you combine these two things, right? You have this black hole where if you have something inside, it cannot escape anymore. And you have this borrowing stuff from the universe business. And what you can, well, this is like, of course, this is a simplified explanation. And, well, if there's any mathematician watching, they'll probably be really angry at me if I don't say this. So, I mean, if you do the proper calculations, that's kind of the result you get. But this is, of course, a kind of, well, the astronomer's explanation, I would say. So what can happen is you have these two particles, and one falls into the black hole, but the other one doesn't, right? So let's say one gets created on the inside of the particle, of the black hole horizon, and the one on the outside. Then the one on the inside is gone. It can never come back to the one on the outside, and they cannot annihilate. So you just have a particle that's left over, and that just flies away. The energy doesn't get like kind of, you don't steal energy from the universe. So actually the black hole loses that energy, and you just get a particle, a random particle that's created and that flies away into the universe. And that's what we call Hawking radiation, after Stephen Hawking, who discovered it. And yeah, so what particles are created? Basically all the particles. I think there's some difference, like depending on their mass, some particles are created more often or less often. But basically you can create all the particles. And actually, I'm wondering about dark matter, but I guess that's another question. Depends on if dark matter can do this annihilation thing. So you would produce all kinds of particles, and basically the black hole would glow a bit. The problem is this glow is really faint, and there's like really hard to detect. So you could like kind of measure this particle if you come really close to a black hole, or if the black hole is really strong in this radiation. But at the moment we did not ever measure this, and it would be really hard to measure it, and we don't expect it to measure it anytime soon at all, because it's just really faint. And at the moment it's more like a theory, but basically most people believe in the theory, because that's just, if you put quantum physics and curved space-time together, you just get this effect. It's, well, not a simple calculation, but it's quite, I think it's quite uncontroversial. Yeah, so I spent a lot of time talking about black holes. If there's anything unclear, like that I said, feel free to just ask follow-up questions in the chat. I'll come to those eventually. So there was something about name. How did astronomers name planets? Right, that's also an interesting question. So we just discussed how you kind of make this appendix for astroplanets, right? So you just add A, B, C, D, or B, C, D, E if you discover planets of stars. Are there other naming things? I mean, obviously the solar system planets are other names.
Yeah, I think sometimes if the star doesn't have a name, I think it can be named after whichever survey discovered it. So you can
Right.
end up with lots of planets which all have the same prefix
Right. I
because
mean,
they're
there
all
you see
discovered by the same
Kepler.
thing, like WASP, for example.
We will have
Or
a postcard from Kepler 16b. So I
yeah,
suppose
sure,
that's
Kepler's a good
the
example.
Kepler
Yeah,
telescope that discovered, I guess, its 16th system or something.
I would imagine so.
And then this is the first planet in the 16th
Yeah,
systems of the Kepler survey.
yes. I guess this system obviously didn't apply to the solar system planets, which are all named after. Is it Roman? Is the
Oh,
Roman
I think
gods,
it's a
right?
mix of Roman and Greek gods, right? I think they're the same anyway, right? They just had different names. Was Jupiter Roman
Yeah,
or Greek? I think Jupiter was
Jupiter's
Roman.
Jupiter's Roman, yeah, and the
But
equivalent for Greek would be Zeus, wouldn't it?
right, you're right. Okay, yeah, I think they're Roman then. Well, okay.
I think I'm not sure about what about Uranus? I don't know about that one.
Okay. um, so what else do we have? Uh, are there any other objects apart from bright dwarfs which have heavier elements that shouldn't be there? Do they get polluted? Yeah, do you get polluted neutron stars, for example?
Yeah, this is a great question because I'm not sure. In
So,
principle, perhaps. I wonder if it's too difficult to detect. I'm not. Yeah, I don't know.
okay,
It's a very interesting thought, and we do
yeah.
know that
So if you want to make it,
planets
sorry, go ahead.
exist around. Yeah, I was just going to point out that in principle it might be possible because I think we know that some neutron stars host planets. So I think the very first exoplanet discovered was discovered around a pulsar, which is a type of neutron star, basically.
Right.
The I think how did they find it? I think they found it by measuring the very slight variations in how long it took the star to rotate.
Oh, that's
I
really
could be wrong
cool.
about that, but I think that's how they discovered the very first exoplanet. I think 1992, give or take a year.
I like this approach.
So maybe give or take 2 years.
Okay.
But I think in principle maybe such a thing could exist. But I wonder if maybe the timescale for pollution to be present in the atmosphere might potentially be too short.
Yeah, so maybe
Obviously,
you want
I'm
to explain this a
speculating a
bit,
bit right
right?
now.
So I think we didn't discuss
Yeah,
this in
sure.
detail yet. So
True,
what happens
yes.
when this planet falls kind of into the white dwarfs?
So, well, firstly, I guess the planet doesn't directly go onto the white dwarf. The exact mechanism is still up for discussion,
Okay.
up for debate. It's an open question, I think, is the phrase that we would use. But I think the idea is that this planet gets too close to the white dwarf, it gets ripped apart because the gravity's too strong, and then the pieces of the planet form a disk around the white dwarf, and the debris in this disk can move onto the white dwarf and fall into the atmosphere. Now, the atmosphere is well, let's look at this the other way around. The white dwarf is very, very dense. It's got a very strong gravitational field, and so it's very strongly stratified, meaning that it will have a hydrogen or helium atmosphere that's extremely pure because anything heavier than hydrogen or helium just falls through. So that's what happens
So
to
it's
all
like
these
in the
elements
ocean,
that
right?
fall in. Sorry?
So it's like in the ocean that kind of everything heavy falls to the ground and you only see the light stuff at the top. Well, like in the ocean
Is
on
that
Earth, kind of.
I guess so. Although in the ocean you can have
Well, I mean,
complicated
imagine a
currents.
clean ocean without all the floating stuff. So ocean with only ocean and rocks.
Yeah, if you imagine rocks in an ocean, it will sink through. But different elements can sink through at different speeds, which is kind of interesting. For a neutron star, I am guessing that would happen very, very quickly.
Okay, yeah.
Potentially, that might be a problem for observing such a thing. I'm sort of speculating here. It can happen quite quickly for white dwarfs as well. So if you look at a helium-dominated white dwarf atmosphere, for the right kinds of elements, you can potentially have elements sinking through on a time scale of, I don't know, something like weeks, or maybe even shorter, which is extremely quick for an astrophysical process, right? Because normally we're used to talking about, especially with white dwarfs, we're talking about things which have existed for billions of years. So then when you see something changing on a timescale of a few weeks potentially, then that's extremely quick.
I think that's also where the excitement came from. We saw Betelgeuse, the star, change by a lot within a few weeks. Because that was of course really exciting. Like usually people would say, oh, a few weeks, like yeah, everything happened in a few weeks. But like for astronomers, a few weeks is like ridiculous. Like you can't even write telescope proposals in a few. Well, I guess you could write in a few weeks, but it's kind of not. Usually the time scales are not much longer.
Yeah, that's a very quick time scale as well. That's pretty exciting. It'd be really cool if we get to see a supernova.
Yeah.
Would it be cool, or would it just be dangerous?
I think it'd be cool and mostly not dangerous. Kind of.
Yeah, it's far enough away, isn't it? Right.
I guess we should. I think it should be kind of similarly bright to the sun. So just some context, because I accidentally got us in a discussion. There's a star called Betelgeuse in the sky. Actually, I forgot where it is. Is it in the?
It's in the constellation of Orion, isn't it?
Okay, yeah, I think the same, Orion. And it changed brightness by a lot, like I don't know, many tens of percent. I think up to 90% or so within a few weeks. And that was really exciting because stuff like this doesn't happen. People thought, oh, maybe it's going to go supernova soon. Like maybe it's kind of imploding or something. And I think the calculations were it would be kind of bright, like almost like the sun, or maybe less like the moon or so, but really obviously visible, and that would of course be really immense. But yeah, it didn't happen, and maybe that's good, maybe that's not so good, but
maybe we're overdue a supernova, aren't we, in the Milky Way? I think.
Yeah.
If you look at how frequently they've happened throughout history, then it's an unlucky coincidence that we haven't actually been able to see one in the galaxy with our modern equipment.
Yeah. Okay.
We've only seen them in other
galaxies. Right. So quite a while ago, we had a question that I overlooked. Why is space so dark? Do you want to say a bit on this?
Yeah. This is interesting. There's a few ways you can look at it, because I know this also comes into there's a cosmological way of looking at this as well, where what's it called? Olber's paradox, I think.
Yes. I can talk about this.
The question of.
I mean, go ahead. I just wanted to offer to talk about the cosmological side, because that's my kind of subfield. Yeah.
Yeah, that would make sense. But I mean, my understanding of it is just that you might imagine that if the universe was really infinite in every direction, then anywhere you looked, there would be a star along your line of sight. And so everywhere you look in the sky, it should be bright with the light of a star. Like you wouldn't see dots in the night sky. The whole thing would just be completely white.
Yeah.
Maybe not.
Exactly that would happen if the universe was infinitely large and infinitely old. So that's kind of one of the key points of this paradoxon, which is why we came up with the Big Bang model, where the universe is actually only 30.8 billion years old. And that's kind of the reason why the star is dark. But yeah, maybe let's talk. So we only see like a few hundred or thousand-ish stars in the night sky. I mean, there are much more in the universe,
with the naked eye, I think. Yeah. Yes. So I guess with the naked eye, I think we see typically a few thousand, which are kind of the nearest stars to us in the Milky Way galaxy. I guess another angle you could look at this question is to say that the gap between stars is very large compared to compared to the stars themselves. So if you think about the distances between planets in the solar system compared to the size of the planets, is a much smaller separation than the stars in the galaxy relative to the sizes of the stars, if that makes sense.
Yeah, right. So when you imagine like going from here to the sun with speed of light would take you 8 minutes, I think. Right? Yeah. Going from here to the nearest star would take you a few years. So that's like isn't it?
Yeah.
And like, I mean, these 8 minutes out of the range, like the size of stars. Stars maybe like, I don't know, less than 1 light minute bright. Broad. Big, I don't know. So the star diameter is like a few light seconds or something. And the distance to another galaxy would be a few light years. So there's a huge distance. And basically everywhere in between there's nothing. There's a whole lot of nothing in the sky.
Yeah.
Which basically means that you cannot see like that many stars. And then stars that are too far away are kind of dim. Or for example, there are kind of dust clouds in between that are still cold, that stop you from seeing stars. Yeah, so there are lots of things that cause. Yeah, basically, and then everywhere there's no light. It's just dark.
Yes, and another thing that might be worth pointing out for this is that the night sky. If you think about it in terms of the galaxies you can see in the night sky with a really good telescope, that's going to get darker as well over time, because as the universe expands, some of these galaxies will disappear beyond the horizon of what we're able to see. So if you wait for long enough, if you're very patient, one day the only galaxy we can see will be our own galaxy.
And I think Andromeda will collide with Andromeda. Yeah. So that will be, I don't know, what was it, Milky Andromeda or Milky Andromeda? I don't know, something like this.
Is there a name for the combined two?
I think there was a name, like something with Milk Andromeda, I think was the name, but I'm not sure. Maybe it was just a meme.
We've got a few billion years. We can come up with something better than Milk Andromeda.
So we got one question by Z2 YouTube. So this question already: did the baryonic matter have a Schwarzschild radius soon after the Big Bang? My answer was space-time was expanding with the entropy of the universe very high. So right, I discussed the black holes, right? And every time you have a lot of matter on a really small kind of area, you can have this kind of effect of having a black hole. And this is kind of a threshold, right? You have to have enough matter inside a small radius so that actually the gravity is large enough. So the Earth could be a black hole if it was small enough. If the Earth was, I think, a few centimeters less large, then it would be a black hole. But because it's also spread out, it's not actually a black hole because the gravity is nowhere strong enough. So on the surface, the mass is high enough, but you're too far away, or it's like too large. And when you would look at the center of the Earth, it would be just too, like, there's not enough mass in a kind of a small area. And so the question is, at the Big Bang, at the kind of very beginning, the universe was really dense. Actually, that's a really good question. So I'm wondering what would be kind of this Schwarzschild radius and what would be the answer, like how that would behave. I think effectively, so yeah, what you would be saying is that, like, even if, like, the universe has a Schwarzschild radius that was kind of larger than the observable universe, we would be all kind of inside this, that's inside this area, and then it would expand. Yeah, that's a really good question. I think I'll look into this afterwards and put a comment below, or make a video on this, because that's really cool.
Yeah, I'm afraid I can't help with this.
Okay, but there's one you can help with me. That was a question.
That's an interesting point, though.
Is there a telescope or future mission that you would like us to answer the question, that you would like to use to answer a question about your research?
I'm not sure exactly how related to my research it is specifically, but I guess the name that springs to mind is the James Webb Space Telescope.
That was also the first one that I thought will probably half the astronomers will probably say James Webb Telescope. So the James Webb Telescope is the successor of Hubble. Actually, I don't know that many things about it, except that it's always delayed. And it's taking quite a while and taking quite a lot of money. But yeah, do you know what's the most recent launch date? Is it still 2021?
I don't. That sounds plausible, but do we believe it?
Well, I mean, it might be the announced launch date. I'm skeptical it will actually launch by then, but we'll see. Yeah, I think.
I'm sure it will.
I think
it's just a bit of a running joke.
I mean, given that it says future mission, I think my answer would be a radio telescope on the backside of the moon. So the reason for this is because, well, the reason why it would be really cool to have such a thing would be because the radio telescopes on Earth are really limited a lot by things like the atmosphere and also humans using radio stuff, right? So phones and all the radio, like all the kind of technology we use, most of the kind of communication uses radio waves. So all these radio waves like fly around all the Earth, and it's really hard to make good observations. And if you'd be on the moon, especially on the backside, it would be kind of facing away from Earth and could make great observations. And it would be, actually, the moon would be really cool to do things. I mean, of course, this is really problematic, because the problem is, I mean, there are no people on the moon to build stuff. But if we eventually go there and can build things, a gravitational wave detector would also be really cool. Because on Earth, you have a problem of earthquakes and, well, trucks driving nearby and stuff like that. That makes your Earth kind of vibrate slightly. And when you have a super, super high sensitivity detector to find gravitational waves going through space, you sadly also find all the trucks and all the earthquakes. So if you build this on the moon, where there are no trucks yet and no earthquakes, it would be much, much easier to, or you could detect much, much fainter gravitational waves that come from much, much further away. So that would be really nice. Yeah. So how does a binary neutron star system form? Oh, do you know about that? I think I heard. I think sorry, I think we are a bit desynchronized.
I'll let you.
I heard Tom explain it a few times, so I can give that explanation.
Yeah.
But if you want to say something, go ahead. We just got an update on James Webb. So the James Webb Telescope, the current tentative time is 2021. So yeah, let's see if that holds true. It would be really cool to have it soon.
Fingers crossed.
Yeah. Okay, so binary systems. Actually, you would think, okay, maybe if you have two stars that kind of, I don't know, fly together, you would get a binary system, and that would be like stick to each other, and they would stay like this. But actually, that's not that easy, and actually much harder, because, well, if you ever try to fly a satellite, which you probably didn't, I didn't either, but I heard people talk about it. And the idea is, well, the thing is that it's really hard actually to hit a planet, or actually kind of slow down or get an orbit around the planet, because if you have a satellite that's really fast and it's kind of flying towards the planet, then what might happen is you just kind of get deflected by the planet, I don't know, make a half turn or something and go on flying away because it's just too fast. So you have to kind of slow down to get somewhere. And a similar thing happens when you, let's say you're a rogue planet flying around cosmos, you find another planet. What probably will happen is you just kind of pass by and maybe get a bit of deflection and go somewhere else. But you won't get bound, is what you say. You won't form a binary system. And the same would be for white dwarfs or neutron stars. So what usually happens is when you have a big cloud of stars that eventually kind of forms a star or 2 or 10 or many, it can happen that you have two stars or two clouds that kind of form really close to each other and directly start as a double star, as a binary star, or even triple star or more. And then you can have this kind of binary star, so both stars will be stars at first, and then the first one will burn out, and then the second one will burn out. Usually the massive one, the larger one, burns out first because it burns its material faster. And so that usually you get kind of an intermediate phase where you have one star feeding off the other, and then you have two kind of dead stars. And that might be two white dwarfs. Actually, I'm not sure if you can have everything, but I think you can have like binary neutron stars, binary black holes, binary like white dwarfs, or combinations of these. Yeah, and right, yeah, I guess that's how they form, right? So they form in the beginning as stars, and then they just burn out, and if they're both in the right mass range, they will both form neutron stars, and then you have them. I think there are not many other ways to form them, at least as far as I'm aware.
Yeah, that would be my thought as well.
Okay. Then I'm a bit more confident in that now. Going near a black hole will slow down time for you.
We could both be wrong.
Yeah, that's true. Well, I guess someone in chat might probably correct us if it happened before. Going near a black hole would slow down time for you. Is there anything that does the reverse, that speeds up time? I think white holes theoretically can do it, but is there any proof that it happens? Okay, so first let me explain this time slowdown thing. There's a thing called relativity, theory of relativity by Einstein, that predicts a whole lot of stuff. Basically, it starts with the fact that speed of light is constant, and Einstein says that acceleration, so let's say you're going down an elevator or up, should be the same as like gravity. So going up an elevator should be not distinguishable at all with any physics instrument, as opposed to standing on a just planet that's just heavier than Earth. So you just have the force on yourself, and it's the same, so the physics should be the same. And if you want, I can go into a bit of more details and give you a few examples. But for now, I just skip the kind of details. And the point is that when you are close to something that's massive, time goes slower for you. And when you are moving fast, time goes slower for you. So let's say I'm just floating in space and I'm not moving, then time runs normal. When I fall down on Earth, time actually runs slower. So if someone was standing on the moon, time would actually go faster for them than for people on Earth. And the other thing, right, if you're going really fast... sorry, want to comment?
Yeah, maybe it's worth pointing out that from your point of view, time seems to be normal. If you're, say, moving really fast,
that's really
you don't
important,
really notice that time's weird for you. Like everything seems normal. You can't tell that something funky is happening. But you seem to be in slow motion from the point of view of someone who's looking at you from a distance.
That's
an outside observer is the phrase that we should use. And the same for if you go near a black hole, an observer would say that you've sort of started going into slow motion for some reason. Like if you're holding a clock, it would look like it's ticking really slowly. But to you, near the black hole, it looks everything looks normal. And you don't know that things are behaving weirdly.
That's so cool, right? So one thing that you, experiment that you should definitely not do is take a clock with you and jump into a black hole and have someone else watch that clock. So you watch the clock, and let's say you time it so that at midnight you fall through the event horizon, to the kind of point of no return, where you cannot go out of the black hole anymore. You just watch the clock, and it happily ticks by midnight, and you look around you, and you do not see anything happen there. You don't notice at all. Like if you don't look at your clock, you don't notice if you pass the event horizon. There's no change for you, for the kind of person who is observing, who is falling in. But for the person who is watching outside, they will see you slowing down, and basically you freeze in. Well, from the outside, it looks kind of that you freeze in time on the event horizon. So you get you don't actually reach it. You just get slower and slower, and you get infinitely slow before the event horizon. So from a person with a telescope outside, looking at your watch, it will never reach midnight. But for you, you can just look at your watch, and you see it going past midnight, and you're like kind of in... I mean, it of course doesn't make sense to say about... Well, that also shows you how time doesn't make sense if you take relativity into account. So you're kind of in a future where the other person can never get. They will never ever in their life, like in the next billion years, they will never see your clock going past midnight. But you just happily look at your clock and see it's going past midnight, and you're inside the black hole. You can't come out again, so don't do that at home. Otherwise, right, so I go a bit off track. We are talking about, this time slowing effect. And the question is, would there be anything that could make this go in the opposite? Make time go faster? I'm not aware of anything that would make this possible, like in theory. Of course, you could go to the moon and your time would go faster for you. Well,
but that's only relative to
Earth, right? But you could not go faster than kind of relative to everybody. I think this would be kind of a thing of like traveling, well, not really traveling to the past, but kind of, right? I mean, you could just, like, if you could do that and wait 100 years and then come back and... I'm not sure how... No, that doesn't make sense. Okay, it's complicated. When you do it, like, in the other way around, it's kind of like traveling into the future, right? People often ask us if time travel is possible. And like, time travel is perfectly easy into the future. It's just really hard in the other direction. So if you want to travel into the future, just go on a rocket, fly with, I don't know, speed of light, a few circles, and you come back and you're in the future, while you only aged like 1 year. Earth went forward, I don't know, a few hundred years. So that's perfectly fine. Just going backwards doesn't work. And I think this time thing also doesn't work in the other direction. Hello to people just joining. Go ahead.
I was wondering if there's any problem in principle with speeding up time. I can't think of any way to actually do it apart from sort of slowing down less. But I mean, something that you mentioned made me think, like, is there a problem with causality if time speeds up for somebody? Because isn't that just the same as...
So I don't see it now, but like,
the scenario you just described, really.
At exercises I did, I think every time you do, like, you assume something that is not like the usual stuff, you always get like paradoxes and like time doesn't work out. So I'm pretty sure you could build a paradox out of this, although I'm not sure exactly how you would do it. Maybe it does work, but I would be skeptical that it
Maybe
works.
we'd have to think about it later.
Maybe you have to like write down equations, but I really don't want to do this on the at the moment because it's really hot here and I can't do calculations. But also,
Yeah, no,
I shouldn't do calculations in
I
public.
could never do maths with people looking.
Yeah, okay. So that's about that. So yeah, not sure about any kind of time slowing down possibility, but I mean it would also be kind of not really that cool, right? I mean you would just it's just kind of you aging quicker and everything else going you aging quicker and everything else going like normal. Yeah, anyway, let's get back to some more basic things. So yeah, just to remind also the new people, if you want to ask us any question about kind of, I don't know, our life, astronomy, science, just put it in the YouTube chat or on Slido, if you want to make a YouTube account, or on the Periscope chat or Facebook chat or whatever, or Twitch chat. Meanwhile, we got one question from Slido a few days ago about quasar stars. So do you want to say a bit about what is a quasar and why it's called quasar, and why do people think it's a star? Well, why did we think it's a star?
I suspect that my understanding of this probably isn't as good as yours, but I believe that a quasar is not really a star. It's I believe it is kind of an abbreviation for a quasi-stellar object, so something that kind of looks like a star. But we now believe that they're actually not stars.
That's correct.
They have a spectrum that kind of looks roughly like a star, meaning that if you look at how much light you get at different frequencies, it kind of resembles a star, which is why it's called a quasi-stellar object, I think.
Okay, yeah.
But then these are, well, okay, we've got an artist impression there now.
Yeah. This impression is of what we think is a quasar, which is actually a black hole. So that's actually really cool. So when you look up in the sky with a good telescope, basically what you see is dots, right? So what you see is kind of, big kind of blur, like big nebulous things, like what we call nebula, and stars, basically points. And these kind of larger patches of white usually are galaxies. For example, the Andromeda galaxy, you might be able to see it with your eye actually if you're in a kind of dark region. It's kind of a right-ish region on the sky, which is kind of a bit of smeared thing. And like various other nebulae are also kind of similar. And actually these are different things, so I should also mention this. There are kind of gas clouds in our own Milky Way that look like smeared things on the sky. And there are galaxies far away that also look from the Earth like smeared things on the sky. But they're totally different in size and shape and everything. Like the one is a billion stars, the other is just a bunch of gas and maybe a few stars, I guess. But anyway, so when you look at these white dots, normally we thought, oh, all those dots are stars, right? Because, well, all the small things we saw were stars because all the galaxies were larger. But what we found out by kind of measuring how far they're away, we found out they are incredibly far away, like much further away than we thought. And the reason was we thought they were really, really bright, so we thought they were quite close. But it turns out they're really far away and they still look so bright. So up close they must be immensely bright. And well, as you said correctly, they were called quasi-stellar objects, short quasar, because they look like stars, but they are not stars. And it turns out, basically what you see is the whole galaxy, but you do not see a whole galaxy. It's like it's brighter than a galaxy. And you don't even see the whole galaxy. All you see is the tiny black hole in the center of the, well, tiny is like 10 to the 9 solar masses, like a billion solar masses is actually quite large. But comparatively quite small, where there's matter like falling into it, so that what we think is like there will be a disk around it, and there's like matter falling in, and there are like jets of matter coming out from all the angular momentum and magnetic fields and all the physics that's going on in there that I don't want to go into now because I'm not at all an expert. But basically they produce a ton of energy. They produce lots of X-ray radiation and, I don't know, light and all the stuff. And it's really, really bright. It's brighter than the galaxy they're in I think almost all cases. So it's really hard even to find that they're actually in a galaxy. And yeah, those are these quasars. And yeah, they kind of look like stars if you just look, oh, it looks like a point, but actually it's far too bright and far too far away to be a star. and it's kind of, yeah, a galaxy. And actually that's a thing that's really useful if you want to do cosmology. So what we want to do in cosmology usually is, we want to find out about really old objects, like really early in the universe, which usually means they're really far away. And far away objects are, well, really dim to us, because the light has to travel and it expands, and the light that reaches us is really small. So what we want to observe are really bright things. And the bright things in the universe are basically supernovae and quasars, and like other kinds of quasar thingy, like all like really small, all like really bright objects. And yeah, I guess most of them are quasars, or they're called in different ways. Like there are things like blazars, and there's things like, how they're called, like Seyfert galaxies, or I think Lyman alpha emitters are all usually quasars. Like there are various things. Actually, that's also interesting story. So let me talk about this for a second. If I miss any questions, let me know. So people had different categories of these bright objects. So there are things like Seyfert galaxies and radio galaxies, which are just the radio astronomers looked into the sky and found these really, really, really bright objects. And that's how they called them. I think Seyfert was some radio astronomer, I think. And other people were doing other observations, like, for example, X-ray observations with, well, other telescopes. And they found other objects. They called them blazar, for example. They were really, like, blazingly bright. And I think there are a few other names that I probably just missed. And what we found out is they're all the same thing. And if you look at this artist impression, it's not that wrong. So you always have this kind of disk of kind of stuff that's falling in, and that's kind of glowing hot. And then you have these jets, these really thin lines going out of this central object, which is always a black hole because there's nothing else that heavy. And these, if this jet happens to point at the Earth, then all this radiation, like this huge amount of radiation, is coming towards us. It's not too dangerous because it's really far away, but it makes it just really, really bright. And that's what we call a blazar. But actually, if the same object was tilted a bit differently, then we would not see this jet, but just kind of the ring. And then we call it Seyfert galaxy, because we would see the radio emission from this jet, but not the jet itself. And depending on how you rotate this object, basically you get different phenomena that are all from the same object and had different names before. So that was actually, I think, a really great discovery. I'm actually not sure who it was.
I wonder if whoever asked about quasars might be interested to know how we know that they're so far away. I imagine this is from looking at the redshift.
Right. So, yeah, I think I mentioned before that the universe is expanding, right? So with the Big Bang, the universe started really small and expanded and expanded. And I mentioned that light has a thing that it loses energy. And this also happens when the universe expands. So if you have a light with a wavelength of, let's say, 1 nanometer, well, 100 nanometers, that's like UV or something.
Yeah.
Good that you check this.
No, I think that sounds right.
I wasn't that sure. I think, yeah, 500 nanometers is like visible light.
Yeah, I think 100 nanometers should be UV.
Okay, so let's say you have this 100 nanometer wavelength, and then the universe expands while this wave is traveling. Then it also expands its wavelength by exactly the same amount that the universe expands. So let's say the universe expands by a factor of 5 from, say, a few billion years after the Big Bang until today. Then this UV wave, wherever it was sent out, expands and expands, and when it arrives today at Earth, it looks like red light. And actually that's why we call it redshift. So when red light is 500 nanometers red? No, it's not red, it's yellow or so, I don't know.
I think
I have a spectrum
500 is
here.
probably green or so. Something around green. That's kind of in the middle, isn't it? It's like 400 to 700. So I'm going to say
my plot doesn't
green,
have labels, so
I don't know.
yeah, it's something in the middle.
Okay, well.
Anyway, yeah, so this light would kind of expand, and before it reaches us, and we would then see it at this frequency. And when you say have blue light, and it would kind of travel a bit, not that much, not times 5, but blue light times, I don't know, 1.5 or so, this blue light would turn into red light. And that's the region where we call this phenomenon redshift, because all the light, that like all the normal light, just gets further towards the red end of the spectrum and gets redder. So we call it redshift. Actually, there's a thing called blue shift. When something is flying towards you and you observe light from it, it actually looks bluer than it is, just because of a similar effect. It's not the expansion of the universe. It's because, well, okay, actually, that's even more similar to everyday phenomenon. You know, when an ambulance drives towards you, it sounds slightly different than it drives away from you. This is because the sound wave gets sent out from the thing that's moving towards you, so then it's kind of shorter. And when it's driving away, the driving away stretches the sound wave, so it gets longer. And the same works with light when something is moving towards or away from you. And that's something you can observe. I think it's relevant if you have these quasars again in these jets. You get like a blue shift because this jet is kind of coming towards you with a really high speed, which affects like how the frequencies looks like.
Yeah. This red shifting and blue shifting is also relevant for finding exoplanets.
There we go. So why did you use it for exoplanets?
Yeah, because so if you have a planet that orbits a star, we often think of the planet just experiencing a gravitational pull from the star, but the star also experiences a gravitational pull from the planet. So as a planet orbits the star, it tugs on the star slightly, meaning that the star is also moving in a little circle. And for half of the time, as it moves around this circle, as you're looking at this star, it's going to be moving away from you. And the other half of the time, it's going to be moving towards you on the other side of the circle. And so it's the same as the ambulance example that you gave. As it's moving away from you, it's the same as the sound wave of the ambulance being stretched out and becoming a lower pitch. And the same thing happens with the star. The light gets stretched out and becomes slightly redder.
Yeah.
And then you get a blue shift on the other side of the circle. And depending on how much the light gets shifted towards either the red or the blue end of the spectrum, that tells you, that allows you to put some constraints on how massive the planet is and how close it is, because what you're really finding out there is kind of what force it's exerting on the star.
That's really cool.
So that's one of the ways that we find exoplanets.
It would be a bit exaggerated. Let's say I look at an exoplanet, and when it's winter there, the star will look a bit bluer, and when it's summer, the sun will look a bit hotter, or vice versa. I mean, I guess you wouldn't be able to see this like with telescope because with eyes, because it's just impossible. Like it's really tiny effect, right? But let's say, right? I mean, if the planet is just going away from us, so it's I don't know. Let's call it winter in their system. It might be a different shade of yellow than when it's summer in their system.
I'm not sure I quite follow where the seasons are.
Never mind. I was just making up seasons on exoplanets. Let's not discuss that. Let's discuss it in the next stream.
I mean, the seasons are just caused by, on Earth at least, it's caused just by how.
Well, I mean, the sun wobbles with seasons, right? Doesn't it?
Sorry.
The sun wobbles with seasons. Like if it would be just the Earth and the sun. Well, okay. I guess it's.
I might have misheard that, but sorry.
Okay, never mind. Let's ignore the season stuff for now. I was making seasons up on exoplanet. Let's leave this to the professional exoplanet people, and not to the cosmologists like me. So yeah, thanks everyone for being here and asking us questions. Thank you, Andy, for your expertise and your great questions and great answers and being so nice and helping me out here.
That's all right.
If you all want to come back next week, Monday, there will be another episode. And if you want to come back earlier, on Tuesday, there will be, so that's tomorrow, right? Yeah. There will be a book club discussing, I think, the book Hidden Figures. So go ahead and check out this YouTube channel. Otherwise, see you again next week. Thank you, everybody. Thank you, Andy. And have a nice evening or day or whatever time.